Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to continue to go over linking structures. In a previous lecture, we started going over linking structures. One of the main concepts of this is we're grouping together data with a link, and this structure is called a node. Linking structures address the problems that we're having with arrays. Linking structures allow growable and shrinkable data structures. However, we do sacrifice random access in order to achieve this. The linking structure that we then addressed was called a linked list. Now, specifically with a linked list, just like a linking structure, you have this thing called a node that contains data and a link. Along with this, there were some special nodes like head, tail, current, and previous, which were used for different purposes as we were developing this linked structure. The major problem that we encountered at the end was the fact that when we created this linked structure, we only created it for one type. So we have to figure out, is there a way that we can create a linked list that can be for any type? Much like an array can have an array of whatever type, our linked list should be whatever type too. To address this, we have to introduce a brand new concept called generics. What a generic does is it acts as a variable for the type. So the way that you would read this is a class of these types. The syntax of using a generic, you would first define the class, and then after that you would use these angle brackets and then put the variable that's going to correspond to this generic type. So if we were going to define a generic linked list class, what we would do is set up a public class generic linked list, and inside of the angle brackets, this is the variable t for the type. More specifically, in Java, the generic type has to be an object type. It has to be derived from a class. This comes from a concept that was introduced very early on, that everything in Java is considered to be an object type. Every time that we have created a class, this class has inherited from the base class object. And in this way, if we assume that everything in Java is considered to be an object type, then whatever is placed inside of this generic must be an object type as well. Taking this concept further, the way that we can basically modify some of the code that we had previously developed is simply change the type. Instead of the data being an integer value, now this generic linked list given this generic type t simply modifies whenever we're referring to the data. Instead of int, it just becomes the type t. The type t is always an object type. Whenever we use double equals or not equals, that should be only referring to the object's memory address. If we're comparing this information, then we should always use the dot equals method, which is a method that is assumed to be developed in every single object. As everything in Java has inherited from the object type, the thing is this dot equals method is already defined inside of the class object. And very similarly, the method toString is defined in every single object as well. It is usually a good idea to override the methods equals and toString and make them specific for that specific type of object. Knowing this now, let's start developing a generic linked list, a linked list that can be any type. So now we're in the code and we have our project set up over here. Let's go ahead and define the generic linked list. We're going to create a new instance of a class, and this time we're going to call it genLL, generic linked list. In order to define this as a generic type, we then put, after the class's identifier, the angle bracket and the type t. Now this becomes a generic linked list of type whatever this type T is. Now with these linking structures, we group together the data and a link to the next thing into another structure called a node. We introduced in an earlier class the idea of internal classes. We're going to use those here as well. Private class list node, and this structure groups together T, data, along with list node link. And just like before, we're going to use the parameterized constructor inside of this. Public list node, and this time we're going to pass in T, a data, and list node, a link. Then we have data point to a data, and link point to a link. You may notice that I'm using different language whenever I'm referring to the assignment operator. Keep this in mind. This type T is the generic object type, which means a data only holds a memory address. By passing this memory address in here, we're saying point this data to this data. Or in other words, assign the memory address stored inside of here to have this point to the same memory address. And also, that's very similar to link. This is a class, which means list node is an object type. A link only corresponds to a memory address, so we're saying store this memory address into this link, which is saying point this link to the object found in this memory address. Now also, in this generic linked list, we're going to go ahead and set up those very specific references, those specific pointers. Private list node head, and this always points to the first element in our list. Private list node current. This is a pointer that allows a programmer who is using this generic linked list to access and modify certain parts of this linked list. Private list node previous. This always refers to the object that is one behind the current. We mostly only use this for remove. Finally, let's go ahead and create our default constructor, public generic linked list, and all we're going to do is assign each one of these pointers to null. Head points to current, points to previous, which points to nothing. Now that we've done all of this, let's see how it can be used. I'm going to go ahead and create a tester class. So I'm going to call this generic linked list tester and include the main method. Now let's say that I wanted to create this generic linked list of type integer. First we'll create a generic linked list, and then inside of the angle brackets we'll say what the type of it will be. In this case, we're going to use integer. Notice that we're not using the lowercase int. The thing is, if we're talking about generics, then the thing inside of these angle brackets has to be an object type. So in order to make an integer linked list, we have to use the wrapper class integer in order to make it. Now what I can do is take ILL and construct it equals a new generic linked list of type integer and a call to the default constructor. And now we've developed an integer linked list. To show off the flexibility of this, let's now create a linked list of doubles. Generic linked list of type double, we'll call it DLL, equals new generic linked list of type double. Taking this even further, we can create a generic linked list of type string. STRLL equals new generic linked list of type string. Now granted, we haven't written the functionality inside of this generic linked list, but already from the beginning, you can see that we can have 3 different versions of the exact same code. Only thing that we've done is abstract out what the data type is. So now that we can create these different generic linked lists given these different types, let's start adding the functionality to this. Let's first approach how to add. Before we get to that, let's go over the concept of how we're going to add elements to this linked list. The concept for adding and removing doesn't change. The only thing that has changed is we're now abstracting the type of information. So if we're adding a new element to the end of the list, what we need to do is first create this new node and assign the data. So first thing, we have created this new instance of this node and assigned the data. Now what we have to do is find the end of the list. If we use a temporary variable and start it at the head, and then always check its .link and see whether or not that's null, then we can indicate where the end of the list is. Whenever we encounter a node where its link is null, that indicates it is at the end of the list. So starting the temp here, we can follow this. It's temp.link. Well, this is a constructed object. This is not null. We haven't found the end of the list, so we have to move temp to point to temp.link. Now we look again. If we follow temp.link, this is not null, move temp forward. Then we follow it again. Temp.link, this is not null, move temp forward. Now we're right here, where if we follow temp.link, this is null. So now what we want to do is assign the memory address right here to refer to this new node that we constructed over here. This is just an identifier. This only holds a memory address. This is also just an identifier. This holds a memory address. So if we follow temp.link points to the new node, this then adds it to the end of our linked list. Once we're outside of that method, the identifier new node no longer exists. However, the new data is still referred to at the end. Nothing changes when we add something. The only thing that we have adjusted is the type. Let's see how this works. Now going back to our code, let's go ahead and create public void add. And this time we're passing in TA data. Whatever this T is, it gets substituted right here. So in this case, it could be integer for this version, so this T becomes an integer. This version is a double, this version is a string. So that means this is substituted as a double for our double and a string for our string. This generic type is a variable for types. Now the first thing that we do is we construct a new instance of this node because that is the container that holds the data and the link to the next node. List node, new node is equal to new list node, and we pass in a data to be assigned. Since we're assuming that we're adding this to the end of the list, this pointer should be null. Now we need to check our head. The head is a very specific pointer that always refers to the first element in our list. If we have an empty list, so in other words, if the head is pointing to nothing, then what we should do is point head and current to the new node and return. Once we have constructed this object, what's stored in this identifier is just a memory address. So then the head and the current simply are assigned the memory address that is right here. Once we are outside of this method, this identifier no longer exists, but we still have head and current referring to where it was constructed. Now, if we didn't have an empty list, then we have to find the end of the list. To do that, we're going to create a temp to first point to the memory address that the head is referring to. While temp.link is not equal to null. Whenever we encounter a node where its link is null, we found the end of the list. But if we haven't found the end of the list, then we need to reassign temp to the memory address found in temp.link. Thus, this moves this temporary variable forward in our linked list. Now, once we're outside of this while loop, this indicates that temp.link is equal to null. We then point temp.link to the memory address new node. And thus, this adds this new node to the end of our linked list. In order to move this ahead a little bit, I'm going to go ahead and develop the method print. That way we can see what is being printed out. Public void print. And we're going to approach this in a very similar way that we approached this. What we're going to start out with is a list node temp and have it point to the head. Now, while temp is not equal to null, all we need to do is system.out.println temp.data and then update temp to point to its neighbor, temp.link. Now that we have this, let's test it out. Going over to our tester, we're going to set up a very similar example. For int I is equal to 4, I is greater than or equal to 0, I minus minus. Now let's add this information to these different structures. ILL.add I. DLL.add. Now, in this case, we do need to typecast I as a double. Normally, we would not have to do this, but because we are using the wrapper classes, we specifically need to do this. strll.add. What I'm going to do here is construct a string, just say str, and then append I to it. Now let's see what happens. ILL.print, DLL.print, STRLL.print. Here are our integers printing out, here are our doubles printing out, and here are the strings printing out. By creating this class generic linked list and then making it generic, what we've done is created this structure that can take on any type. However, the functionality is still the exact same. The functionality does not depend on the type of data. It's still doing the exact same thing. And now, because we're using generics with this, we have the flexibility of creating one data structure that can be any type. Let's develop some more methods for our generic linked list. For instance, let's do that add after current. Once again, the concept does not change. Public void add after current. T, a data. Now this can allow us to add an element in the middle of this linked list. So first, if current is equal to null, that means current is currently not referring to anything, so we can't really add anything after it. But if it is, we create a list node, new node, is equal to new list node. We construct this, and then we add the data to the node. And as we're adding this after current, we want this new node to point to where current is currently pointing at. How we do that is we access current.link. And now this new node has the data assigned and it's pointing to where current is currently pointing to. After that, we readjust current.link to now point to the new node, and thus we've added this new node after current and still maintain the rest of the list. Now, current is a movable pointer. It is used when people need to access and modify data that is inside of this linked list. So in order to allow them to access the data, we need to create basically an accessor for this pointer. The way that we do that, public. Now, the data that we're returning is the generic type T, and we're going to call this getCurrent. The type T is assumed to be an object type. So if current is equal to null, so it doesn't exist, then we need to return nothing, null. However, if that's not true, we return current.data. Now we need to be able to set the data. Public void set current TA data. Now, just like before, I'll argue that this data probably shouldn't be null. So if we do pass in if a data is equal to null, we need to return. We're going to assume that the data in every one of these nodes is valid and has been constructed. Now, that's not the only case. If that's true, or current is also equal to null, then we need to return. We can't set information that doesn't exist. Now, as long as neither of these are true, then what we can do is just go ahead and assign current.data to now point to a data. Now we can access and modify the information at the pointer current. But currently, current is only going to point to the head element. We need to be able to move it around. In order to move the current forward, we're going to create a method called public void goToNext. And once again, if current is equal to null, then we need to return because we can't go to next. However, if that's not the case, we're going to take previous and have that point to where current currently is. Then we point current to its neighbor, current.link. Now current can move forward, but current cannot move backwards. To address this, we're going to create public void reset, which is going to point current to the head and also previous to null. As I am not calling a property or a method from this list node, I don't need to check whether or not it's null. If current was null and head was also null, it doesn't matter. It's just null gets assigned to null. Now also, outside of this, a programmer needs to be able to understand if we have more. So if we're calling goToNext, we need to indicate if we can go to next. The way that we do that is by comparing current to whether or not it has been constructed. Public Boolean has more, and we're just going to return current is not equal to null. As long as current is not pointing to nothing, then we can assume that we have more. Now that we have that, let's address how to remove information from this linked list. Now let's assume again that we're going to remove whatever current is referring to. The concept for this doesn't change. Now, if it is the head, then all we have to do is move the head pointer forward and also make sure that current is still referring to the new head. If current is not at the head, then all we need to do is skip over the reference. So, starting from right here, if we're going to delete current, the thing is we take previous.link and assign that to where current is pointing to. So now, previous.link needs to refer to current.link, this object right here, and thus it'll point over top of it. Then we need to update the current by setting current is equal to current.link. Now this node is unreachable, and because Java is a memory managed language, it has a garbage collector which goes along and sees that this data is unreachable, and so it simply removes it. Starting right here, public void remove current. Now, if current is pointing to the head, so this means in this identifier, this memory address matches the memory address in the head. That means current is pointing to the same object that head is also pointing to. If this is the case, then what we need to do is take head and point it to head.link, and then assign current to point to the new head. Now, if current is not pointing to the head, this indicates that current is somewhere else in our linked list. Else. In this case, we have what was in the demonstration, where we first take previous.link. Previous.link is always referring to current, because previous is assumed to be one node behind current. Previous.link is the exact same address as what's stored inside of current. Now, if we reassign this to current.link, this now points over top of where current is. Then we move current is equal to current.link. So now, after all of this, we have created this linking structure that can be any generic type. We've created this linking structure where we can add data to it. We can remove data from it. We can access information at any given spot. We can mutate information at any given spot. We can also print out all of the information that is currently stored inside of this. All of this is the most basic functionality that we really need to create some of these linked lists. However, these data structures are your own. You should create them how you see fit. If you believe that there should be extra methods in there, then you should write them. Like, for instance, maybe it's just not enough to have this current. Maybe what we want to do is get a current given a certain index or a certain value. Maybe it makes sense to write functionality that will indicate if an element in this linked list is already in there, like a contains method. It might be beneficial to write a method that examines every element of one linked list compared to another one to see if they're equal. It might be useful to write a goToPrevious method instead of just having a reset. There are a lot of different ways that we can approach this. And once again, these are your data structures to use. Foundationally, we start out with arrays. And now we have these linking structures that we can create on our own. And also, speaking of that, there are different versions of these linked lists as well. Now, what we have been using so far is called a singly linked list. The reason being is each one of the nodes has a single link that refers to the next node. Other variations of these kinds of linked lists would be called a doubly linked list. So in a doubly linked list, you would have in each one of the nodes a forward and a previous pointer. In addition to that, you could also create what's called a circular linked list, where the last element always refers to the first. And you can even have a singly and doubly version of those as well. Each one of these has pros and cons. They have trade-offs that we have to be mindful of. That way we are using the most appropriate data structure to address our problems. In the last couple of lectures, we've been addressing linking structures, and more specifically, the linked list. The linked list is really great if you want to have a resizable data structure and you don't really care if you have random access. The array gives you random access but not resizability. Which one is more appropriate for our problem? In future classes, we're going to be using these foundational data structures to make more specific and more advanced versions of data structures. And with all that being said, I'll see you next time.